Alright, so this is section 6.4, which is arc length and surfaces of revolution. We're going to look at arc length today, we'll look at surfaces of revolution tomorrow. So I understand that this notes paper is a little bit blurry, but you can still read it if you squint your eyes. It's hard to read, but you can read it. So it says a rectifiable curve is one that has a finite arc length. So essentially, it's not unbounded and it doesn't go to infinity or anything like that. So it has arc length that you can measure, essentially. A sufficient condition for the graph of a function to be rectifiable between some a f of a and b f of b is that f prime has to be continuous on a to b, the closed interval. It says such a function is continuously differentiable on the closed interval from a to b, and its graph on the closed interval from a to b is a smooth curve. So there are two formulas to help find arc length. The first one is if you have your function in terms of x, so y equals some function of x, and if it represents a smooth curve on the closed interval from a to b, then the arc length of f between a and b is this integral. So s is the variable we use to represent arc length. So s equals the integral from a to b of the square root of 1 plus the first derivative of f squared dx. And then vice versa, if you have your integral in terms of y, so it's x equals some function in terms of y, then the formula for the arc length is the integral from c to d, where c and d are y values, of the square root of 1 plus the first derivative of g with respect to y, squared dy. So down here is an example. We're actually going to look at the examples in the book. I just wanted to fill this one in for you guys. So it's a function in terms of x, a function of y equals in terms of x. So these are the x values from 0 to 4. So if you set it all up, the first derivative of this function, 2x cubed minus x squared plus 5x minus 1. The first derivative is 6x squared minus 2x plus 5. So if you plug that into the formula for arc length and you put it into your calculator, you get 132.141. This one's a little bit difficult to solve by hand, so we'll just do that one in the calculator. We'll solve the rest of them by hand. So let's look at the first example in your book. We're actually going to skip over example 1, which is on page 436. And just the reason is that's just a general solution to any linear equation, so you can look over that one, but it doesn't have any concrete answer or solution to it, so we're going to skip that one. And we're going to look at example number 2. Alright, so our first example is on page 437. It's example number 2. So we're trying to find the arc length of this equation, y equals x cubed over 6 plus 1 over 2x, on the interval from 1/2 to 2. So I can start setting up my arc length formula. S equals the square root, the integral of the square root from 1/2 to 2 of 1 plus, and then in here is the first derivative of what y would be. So the first derivative of y, if you find the first derivative of x cubed over 6, you get 3x squared over 6, which is the same thing as x squared over 2. And then the first derivative of 1 over 2x is, if you bring the x to the top with the x to the negative 1 power, you get negative 1, so I'll actually change that to a negative. You get negative 1 over 2x to the negative 2, or times to the negative 2, so when you move it to the bottom it would be negative. Let me change this just a little bit so it's clearer. There we go. Dx. So if you look at this squared part of my square root, I can actually take out a 1/2. So if you take out a 1/2, and I'm not going to write the limits of integration for right now, we'll come back to those later. If you take out a 1/2, you get 1/2 times x squared minus 1 over x squared, and all of that is being squared, dx. And the reason I'm doing that is just because it's going to make it easier to multiply out, and it'll make it easier as well to simplify it later. So if I square that, I get the integral of 1 plus 1/2 squared is 1/4. X squared minus 1 over x squared is x to the 4th. Then for the inner outer of that FOIL, you get x squared times negative 1 over x squared, which is negative 1 and negative 1, so that's negative 2. And then for the last term, you get 1 over x squared times itself, which would be 1 over x to the 4th dx. So if you want to combine that 1 into there, I can say that if I'm going to combine it into that function, I have to make it like a 4 over 4. So if I change the 1 into like a 4 over 4 kind of thing. And that way, when I put it into the function and combine it with this 2, I can leave the bottom 4 outside as if I was factoring out that 4 on the bottom. So when I do that, I get 1/4 times x to the 4th. When I push that equivalent of 1, the 4 over 4, when I push the top of the 4 in there, I get -2 plus 4, which is plus 2, plus 1 over x to the 4th dx. This square root simplifies a little bit. I get 1/4. Then this is a perfect square. It's actually x squared plus 1 over x squared. And this is now a perfect square. So the square root of 1/4 times x squared plus 1 over x squared to the second power is 1/2. Oops. Still looking at the integral, by the way. 1/2 times x squared plus 1 over x squared dx. And now this should be fairly simple to integrate. So when I integrate it, I can bring the 1/2 out front as a constant, and then I get x cubed over 3 minus 1 over x as the integral of 1 over x squared. And I'm evaluating that from 1/2 to 2. If I plug in 2 and I simplify a little bit, I get 1/2 times 13 over 6 plus 47 over 24. I would definitely suggest that you don't jump straight ahead to that. Actually work it out just so that you can convince yourself of that, and make sure that you're getting the same answers as I am, but you might just take a few more steps to make sure that you understand why those are the answers. And then when you simplify all of that, you get 33 over 16. So that was the length of the arc from 1/2 to 2 of the equation that we were given. Alright, we're only going to do 2 more examples tonight. It's kind of a short one, so let's look at example number 3. Alright, so here's example number 3. Notice that we don't have any of our variables solved for. We don't have y solved for by itself, nor do we have x solved for by itself. But if you look at it, it probably looks easier to solve for y by itself. I'm sorry, the other way around, to solve for x by itself. So if we take the square root of both of those, we get that y minus 1 cubed, and then the square root, so I'm just going to put to the 3/2 power, equals x, and that should be plus or minus that we look at over there. So now we have x in terms of y. One thing, it doesn't specifically say this, but when you're given an interval, unless it specifically says that they are y values, don't assume that they are. Always assume that they're x values. So these are actually x values, which means that we need to convert them into y values so that we can plug it into our arc length formula, because we're going to need new limits of integration now that we're dealing in terms of y. So we're going to have 1 plus, we're going to take the positive, well, we're going to take the derivative of this first, but you'll see why. So here, let me back up a step. So first let's look at the x values. So if I plug in 0 here, alright, and I'm trying to solve for what y would equal, 0 squared is just 0, and then if I take the cubed root of both sides, I still get 0, and so I have y minus 1 equals 0, and then if I add 1 over to the other side, I get that y equals 1. So y equals 1 when x equals 0. And then when x equals 8, if I square 8, so again I'm plugging it in there on the right hand side, if I square 8 I get 64. If I take the cubed root of both sides, the cubed root of 64 is 4. And then if I add 1 over to the other side, I get that y would equal 5 when x equals 8. So here are my new limits of integration that I'm going to be looking at. So I first need to find the derivative, dx dy. Now because I'm looking at positive, all the positive y values, obviously, from 1 to 5, those are positive. So I'm going to look at the positive side of the interval, so I'm just going to look at positive y minus 1 to the 3/2 power. So when I take the derivative, I get 3/2 times y minus 1 to the 1/2 power, and then the derivative of what's on the inside is just 1, so that's the derivative. And now I can plug it into my arc length formula. So I get s equals the integral from 1 to 5, those are my limits of integration on y, times the square root of 1 plus 3/2 times y minus 1 to the 1/2 squared dy. So I have 1 plus, when you square 3/2 you get 9/4. When you square y minus 1 to the 1/2 you get y minus 1. When you distribute the 9/4 you get 1 plus 9/4 y minus 9/4 dy. When you combine the 1 with the negative 9/4, that would be 4/4 minus 9/4 is, you have the 9/4y, and then the 1 minus 9/4 gives you negative 5/4 dy. And of course, to simplify it a little bit more, you can pull out that 1/4 from the fraction. So you have the integral of the square root of 1/4 times 9y minus 5 dy. So let me erase some of this stuff just so we have more room to write. Alright, so the 1/4 is a perfect square. That becomes 1/2, and I can actually pull it out of the integral since it's a constant. So that's 1/2 times the integral from 1 to 5 of the square root of 9y minus 5 dy. So now we can actually take the integral. So I can use u substitution if I wanted to, so I'm going to kind of skip that step and just kind of think about it as I go into it. But if you need to actually see it written out, definitely set u equal to 9y and figure out how we're doing this next piece. So if I integrate this, I have 9y minus 5. It was to the power of 1/2, so now it's to the power of 3/2, because I'm bumping it up by 1, divided by 3/2. And then for that inside, I have to account for the 9, because the derivative of the 9y would be 9, so I have to account for it by multiplying by 1/9. Again, if you don't see why we're getting that 1/9 or how we're getting that 1/9, make sure that you go back through the u substitution and figure out how it's done that way. So if I simplify this a little bit, this is all from 1 to 5, by the way. So I get 1/2 times 1/9 is 1/18. So I have 1/18 times that fraction, bring it up to the top, that's 2/3, times 9y minus 5 to the 3/2. From 1 to 5. 2/3 times 1/18 gives me 1/27. And then if I do the first fundamental theorem of calculus, I plug in f of b minus f of a. So that's 9 times 5 is 45, minus 5 is 40, to the power of 3/2. That's f of a, minus f of b. So if I plug in 1, I get 9 minus 5, that's 4 to the power of 3/2. And if I put all of this into a calculator and simplify it, I should get 9.073, about equal to 9.073. Which is the length of that arc for the y values. Alright, we're only going to look at one more. We're going to look at example number 4. So go ahead and turn your book over to page 438. Alright, and this is the last example. This is example 3. So I have y in terms of x, so I don't really have to do much changing, and I have my limits of integration from x equals 0 to x equals pi over 4. So if I have to find dy dx, the derivative of ln of cosine x is 1 over cosine x times the derivative of cosine x, which is negative sine of x. Which, if you simplify that, you get negative tangent of x. So when I plug that into my formula for arc length, I get s equals the integral from 0 to pi over 4 of the square root of 1 plus negative tangent squared of x, or x squared I should say, dx. And if I square negative tangent x, I get positive tangent squared x, and 1 plus tangent squared x is actually equal to secant squared x. So this is secant squared x dx. And the square root of secant squared x is the integral of secant x dx. Of course, this is all still from 0 to pi over 4. So, the integral of secant x dx is actually the natural log of the absolute value of secant x plus tangent x from 0 to pi over 4. So if I plug in f of b minus f of a, I get ln of secant of pi over 4, which is 2 over radical 2, and when you rationalize that, you get radical 2, plus tangent of tangent of pi over 4, which is 1, minus f of a, so ln of secant of 0 is equal to 1, because that's 1 over cosine, which is 1 over 1, plus tangent of 0, and tangent of 0 is equal to 0, so that's just 0. So it looks like that. When you plug that into a calculator, you get approximately equal to 0.881. And that's the arc length for that curve. So, essentially the formula and just making is the hardest part of this, making sure that you know that what that formula is, and then from there you just have to simplify everything as much as you can, take the integral of it, and then plug in the numbers, and you can find the arc length fairly easily. It's also important to note whether or not you're dealing with x's in terms of y's or y's in terms of x's, just so that you know which one to use and where or which limits of integration you should use, whether or not they're x values or y values. Alright, that's it for today.